All right, let's do an example of momentum conservation. All right, here's the problem. We'll draw a diagram here in just a second. So we have a 500-gram ball of clay that is thrown at a stationary frictionless cart at 10 meters per second. This is the velocity of the throw. And it sticks to it. It sticks to the cart. If the mass of the cart is 1 kilogram, what is its final velocity? And you can ignore gravity. That will make this simpler. Okay, so I'm going to erase all this and draw a diagram. So we have our cart sitting stationary with a mass of 1 kilogram. We have a ball of clay thrown at the cart at 10 meters per second. And this cart is sitting on a surface with no gravity, although if there's no, or excuse me, with no friction, although if there's no gravity, friction isn't going to matter anyway. So, okay, so this is what our problem looks like in the beginning. Now, at the end, what happens? Well, our ball of clay hits and sticks to the cart. We will draw it stuck on there. And the claim is that the cart has some final velocity that we want to find. You could imagine doing this in real life. If you throw something at something that's not moving and it hits it, it's going to push that thing to the right. So it at least kind of should make sense that the cart is moving to the right at the end. Okay, so to justify whether we can use momentum conservation, we should start by looking at what our system is and then seeing if our system follows these rules of momentum conservation. Okay, so our system here needs to include both the ball and the cart. So our system is like this whole thing. If we look at the system of just the ball, well, then there is an external force on the ball, right? When the ball hits the cart pushes back on the ball, and that is a force on the ball. So if that is external to our system, that is an external force. Momentum is not conserved. But if we draw a system like this, a system of the ball and the cart, whatever force happens when the ball first hits the cart, that force is now internal to our system, right? Our system is this whole thing. This is a force between two different parts of our system. And so internal forces do not affect momentum conservation. Momentum is only not conserved if there are net external forces. And so that's okay. This would still obey momentum conservation. So on our whole system, are there any external forces? Well, the problem said ignore gravity, so there's no gravity. And our cart is touching a frictionless surface, so there's no friction. So there are no other forces on our system at all, actually. We could just as easily have drawn this floating in space with no floor underneath it at all, just, with the floor having a frictionless surface is easier to imagine than maybe two things floating with no gravity. So that's why we have it with a surface. Anyway, so if our system is the ball and the cart, there are no external forces, which means that our momentum is conserved. So what does it mean for our momentum to be conserved? That means the sum of all of our momentum at the beginning is equal to the sum of all of our momentum at the end. So let's start by figuring out how much momentum we have at the beginning. I erased the mass of the ball. This was 500 grams. So P initial of the ball is equal to mv. So that's 10 times 500 grams is 0.5 kilograms. So this is 5 kilogram meters per second. P initial of the cart is 1 kilogram times v equals 0, which is 0. So our total initial momentum is just 0 plus 5, which equals 5 kilogram meters per second. One down. Our final momentum. Okay, so for this, we want to find this final velocity using our final momentum. It is important that the ball sticks to the cart. Because that means that if it hits it and sticks, and if it sticks to it, they're moving together at the same velocity, right? That's what sticking together means here. So the ball sticks to the cart. That means V final ball equals V final cart. This is just kind of a common sense sort of thing. I don't really have a better argument for it than that. So these are both moving with the same final velocity. So at the end, we have our ball, we have the momentum of the ball, which is equal to m 0.5 kilograms times V final. And we have the momentum of the cart, which is equal to our 1 kilogram times V final. So our final momentum here is equal to 0.5 V final plus 1 V final, which is equal to 1.5 times V final. Okay, solving for V final now, we have 5 kilogram meters per second equals 1.5 kilograms, right? This is my mass there, times V final. So V final is equal to 5 over 1.5, which is equal to 3.33 meters per second. And there we have it. That is our final answer. The ball thrown at 10 meters per second hits the cart, sticks to it, and they both move to the right at a lower velocity at 3.33 meters per second to the right. All right, so that's what this looks like. Initial momentum equals final momentum. We solve for the part that we don't know. Okay, so let's look at this in terms of energy just for a second now. So we've done the momentum part. We've solved the momentum. We've used the momentum to get the final velocity. What is going on with energy? Well, we definitely have kinetic energy at the beginning. We definitely have kinetic energy at the end. But could we have solved this problem with energy to begin with? Well, the answer is no, because something is happening with the force between the ball and the cart. And that is, this force between those is not a conservative force. And the way we can see that, well, the way that we knew not to solve it with energy was that we were not told that that was a conservative force, so it would not have been safe to do so. But here's one other clue that we have, I guess. So I said that this was a ball of clay, right? So that's something soft and kind of sticky. And when that clay hits the cart, it is going to smush and deform and change its shape. And changing the shape of that object takes energy. Like, you have to exert, if you were to imagine deforming a piece of clay, you push on it with some force for some distance. You are doing work, literal F times D physics 106 work on that piece of clay to change its shape. But you don't get that energy back. This is not energy stored in the potential energy of the clay. This is something more like friction, where you do the work and the energy disappears and it's gone forever because you've put work into increasing the temperature of that piece of clay by some tiny fraction of a degree. So the thing to realize here is that anytime you have something soft whose shape is being permanently deformed, or I shouldn't say permanently, we could push it back, but that would take even more work for us to put in. So something that deforms and is not going to automatically spring back on its own, that is indicative of a non-conservative force, of a force where mechanical energy is going to be lost. And given that it sticks to it, we actually know enough to figure out exactly how much energy is lost. And I'll show you how. So let's look at the energy again. So at the beginning here, we know these two parts have, well, we can look at the kinetic energy of these parts, right? Here, the kinetic energy of our cart is 0. Here, the kinetic energy of our ball is 1/2 times m times v squared. So 1/2 times 0.5 times 10 squared. That is 25 joules of kinetic energy. And at the end here, so 25 plus 0 gives us a total kinetic energy of 25 joules at the beginning. So this is the initial kinetic energy. At the end here, we have two objects, both moving at 3.33 meters per second. So we have 1/2 times m of the ball times v squared plus 1/2 times m of the cart times v squared. And so our total kinetic energy at the end is equal to, if we type this in the calculator, we get 8.33 joules. So we start with 25 joules. Our clay ball mashes against the cart, and we end up with 8.33 joules. So in other words, our kinetic energy has decreased by 16.7 joules. That is 25 minus 8.3. And none of this is hidden in any potential energy. Like there's no spring that gets compressed. The cart doesn't go up a hill. This is all energy lost to the interaction of this clay ball and the cart. So in other words, this energy is lost. It is not, like I said, not hidden as some potential energy. Anyway, so this is a good kind of introduction to momentum conservation problems, I think. And we'll have more like this to look at, and being able to analyze it in terms of momentum and then look at the energy at the end, I think is really important, because it's neat to see in this situation exactly how much energy we lose and why. You know, what non-conservative force is causing us to lose that energy.